Hello all, welcome to my channel PSA Tech Classroom. Now in this video I'm going to teach you the analog filter designing techniques. As we discussed in the previous lecture, I told you that there are two approximation methods for designing the digital filters. One is the Butterwoth approximation method and second one is the Chebyshev approximation method. So once again I'm repeating you, these two are the two approximation methods for designing the analog filters. Okay, now in this video lecture, first of all I would like to concentrate on the Butterworth approximation method. So it means that in this lecture I am going to teach you how to design a low pass Butterworth filter, or I can say that I'm going to design a low pass filter using the Butterworth approximation method. Okay, so before going to the Butterworth approximation method, let us concentrate on the Butterworth polynomials for the omega is equal to 1 radians per second. Okay, so these are the order of the Butterworth polynomials. So this is the n is indicating the order of the filter, and if the order of the filter is 1, the Butterworth in the Butterworth polynomial you have to take the denominator of h of s as s plus 1, and 2 is equal to, if it is 2, s square plus root 2s plus 1, and if it is 3, s plus 1 into s square plus s plus 1, and 4, s square plus 0.76537 s plus 1 into s square plus 1.8477 plus 77 s plus 1. So this is the value of the denominator of h of s for the order n. Okay, now after four things in the examination point of view, the students has to remember these values. Okay, after this I would like to tell you what is the importance of order n. What is n value? The n value is nothing but it is the order of the filter. For example, as I told you, we are going to design the filter, right? So the filter is having some order, the first order filter or the second order filter and the third order filter, like that. So what is the importance of the order? The order gives you the number of poles required for the filter, and the poles are defined in the transfer function and the stability of the filter. Once again I am repeating you, the order of the filter will be used to define the poles of the filter, and the poles of the filter are defined in the transfer function and the stability of the filter. Why it is transfer function? Because the transfer function is the function of the filter. So you are designing the filter means you are deriving the transfer function of the filter. So this is the about the significance of the order. Now let us go the main steps of designing the analog Butterworth filter. See, the students, if you are knowing these steps, then it will be easy for you for designing any of the filter. In the examinations they won't ask you what are the steps for the designing the Butterworth filter. They will ask you design the filter with the given specifications. It means that they will ask you for doing the problem. So for doing the problem you need to know the procedure of defining the or designing the filter. So first of all, if the given specifications are given, you have to find out the order of the filter. Then if you got the order of the filter in the fractional number or the number, then you have to make it the next integer value, and it means that if you got order n is equal to 2.7 or 3.7, like that, you have to round up to the next integer. If you got 2.7, make it 3. If you got 3.7, make it 4. Okay, next, after that rounding off to the next integer value, now find the transfer function h of s for omega c is equal to 1 radians per second. Omega c is nothing but the cutoff frequency. So why we are taking the omega c is equal to 1 radians per second is for simplification purpose. This technically we are calling it as a normalization. For simplification of the mathematical tools, we are taking the omega c is equal to 1 radians per second. So these Butterworth polynomials also, which we have derived, is also taken into considerations as omega c is equal to 1 radians per second. So after that we are scaling that to the our required cutoff frequency. After that, first of all we will derive the h of s for the omega c is equal to 1 radians per second. After that, again for the denormalization purpose, we are scaling that into the normal filter by substituting the s by omega c value. Omega c value is the required filter. Okay, so this is called as the normalization process. Okay, these are the steps for doing the analog filter. Now after learning these filters, now let us go to the important. This is the main important topic of the Butterworth filter designing. As we know the designing steps for it, now we have to know what is the formula for calculating the order n. If you know this formula and if you know the procedure, then it will be very useful for you for attempting the question, right? So order n is greater than or equal to log of 10 power under root 10 power 0.1 into alpha s minus 1 divided by 10 power 0.1 into alpha p minus 1 whole divided by log omega s by omega p. Omega s is the stop band frequency, omega p is the pass band frequency in radians per second, whereas alpha s and alpha p are the attenuations in the stop band and as well as the pass band. And you are 10 power 0.1 into alpha s minus 1 under root will be called as a lambda value, and in this denominator is called as a epsilon value, so that this formula will be reduced to log lambda by epsilon by log omega s by omega p. So I told you epsilon is equal to 10 power 0.1 into alpha p minus 1 whole power 1 by 2. 1 by 2 is nothing but under root also you can say, okay, like that. Next, after calculating the n value, next is you have to find out the poles. So poles sk is equal to omega c into e power j pi k. So it means here you have to calculate the omega c value. Omega c is the cutoff frequency and e power j pi k. The k value is ranging from 1 to n. The k value is ranging from 1 to n. So now omega c value you will get by omega p by 10 power 0.1 alpha p minus 1 whole power 1 by 2n, or from the stop band frequency also you can evaluate. So these two are the formulas for calculating the omega c. After that, the pi k value is equal to pi by 2 plus 2k minus 1 into pi by 2n, where k is equal to k is ranging from 1 to n, and where n is the order of the filter. Next, after knowing the n value, after knowing the poles values, then we can easily calculate the transfer function h of s. The transfer function h of s is equal to numerator by denominator. So numerator is nothing but numerator is equal to omega c value. Omega c value is the cutoff frequency. We are taking it as a 1 for everything. Next is denominator is nothing but the normalized Butterworth polynomial. So in the beginning of the class only I told you the Butterworth polynomial for the denominator of the h of s. If you got 2 value, then substitute s square plus root 2s plus 1. If you got 3 value, s plus 1 into s square plus 1, and if you got 4 value, this value. Okay, so after knowing all these things, we can easily design the filter. In the next class, I would like to teach you how to do the problems based upon the Butterworth approximation method. So, but for doing the problems, knowing this about the formulas and the procedure is compulsory. If you know the procedure and formulas, it will be very useful for you for designing the filter. Thank you.